Very good morning.
Good morning, sir.
Let us wait for 2 more minutes. Meanwhile, others can join us. Okay, then
Okay, sir.
we'll start today's laboratory session. What we did in last laboratory session?
Sir, experiment 5, strain gauge.
Okay, experiment five. So today we will see two or three more experiments because our term end is approaching. Okay, so we will see more experiments in today's laboratory session. Okay, shall I start? Yes, 5 number and 13 number. Hello.
Yes, sir.
Yes, sir.
Basically, I would like to say few things at this moment. As per the instruction, in first week of May, your submission Viva is scheduled. Submission and Viva is scheduled. Okay.
Okay.
I'm just sharing list of experiment, entire list of experiment with you people. Just go through the chat window. Okay, let me reduce the size. Font size medium, no bold. Let me change color to so it is expected that you people should complete your file work and submit it to me uh, before term end. Wait, I'm pasting that message in chat window. Total 10 experiments are there. Are you able to see the message in chat window, dear students?
Yes, sir.
Okay, so it is our list of experiments. Okay, now let me start. So we have completed up to strain gauge, am I right? Hello?
Yes, sir.
So our next experiment is to understand the working of Wheatstone bridge. Am I right?
Yes, sir. Experiment 6.
So I have shared my screen with you people. Is it visible? Dear students,
No, sir.
is it visible?
It's loading now.
Now,
Loading, sir.
is it?
No, sir. Not yet. So now it is visible.
Okay. So it's our laboratory for electronic measurement. Basically, this subject is having name EMI. Okay, electronic measurement and instrumentation laboratory. It was old title, and the university has revised this title, and just they are giving as a laboratory, electronic measurement laboratory. Today, our first experiment having title to study and understand the working of Wheatstone bridge. Okay, so over here we are going to see about aim theory and simulation link. So do you think we are going to study about this kind of bridge?
No, sir.
Are you aware about the bridge as shown over here in this diagram? It is very famous bridge.
Yes, sir.
What is the name of this bridge? Probably at the time of your junior KG or senior KG, means kindergarten time.
London.
Yeah, London Bridge. London Bridge is falling down. Okay, so over here we are not going to study about this type of bridge. Our bridge is one type of circuit which is widely used in instrumentation. Okay, so that bridge is nothing but Wheatstone bridge. Okay, I have added one animated video of is generally I am placing one video so that you can understand this concept easily. So I have placed one video over here. I will play this video twice, and if you are facing any difficulty, then please let me know. Even in between, I will explain some fundamentals. First, tell me, is it audible or not?
Wheatstone Bridge.
Is it audible?
Yes, sir.
Okay.
Definition of Wheatstone Bridge. A bridge for measuring electrical resistance that consists of a conductor joining two branches of a circuit. Biographical note for Wheatstone Bridge. Wheatstone, Sir Charles, 1802 to 1875, British physicist. Wheatstone was professor of experimental philosophy at King's College, London. He is remembered for his researches in electricity, sound, and light. The Wheatstone Bridge is a specific circuit that is used for measuring resistances and has many and varied applications in instrumentation systems. There are two basic modes of bridge operation. In one mode, the bridge can be used to determine the value of an unknown resistance to a high degree of accuracy by comparing it with an accurately known resistance. If this bridge output voltage is displayed on a meter, then the matter can be calibrated in terms of the measured variable, temperature, light, expansion, etc. A variation of the resistive type Wheatstone bridge is the reactive type or AC bridge. This type of bridge is used to measure capacitance and inductance values. The Wheatstone bridge network is based on the parallel resistance circuit as shown in Figure 1. Figure 1. Parallel resistance network. The operation of the Wheatstone bridge is based on bringing point B and D to the same electric potential, that is, EBD equals to 0, by adjusting the variable resistor. For the Wheatstone bridge, point B and D are generally stretched outward, giving the characteristics diamond-shaped bridge circuit shown in Figure 2.
I am playing this video again. Listen it carefully.
Wheatstone Bridge. Definition of Wheatstone Bridge. A bridge for measuring electrical resistance that consists of a conductor joining two branches of a circuit. Biographical note for Wheatstone Bridge. Wheatstone, Sir Charles, 1802 to 1875, British physicist. Wheatstone was professor of experimental philosophy at King's College, London. He is remembered for his researches in electricity, sound, and light. The Wheatstone bridge is a specific circuit that is used for measuring resistances and has many and varied applications in instrumentation systems. There are two basic modes of bridge operation. In one mode, the bridge can be used to determine the value of an unknown resistance to a high degree of accuracy by comparing it with an accurately known resistance. If this bridge output voltage is displayed on a meter, then the matter can be calibrated in terms of the measured variable, temperature, light, expansion, etc. A variation of the resistive type Wheatstone bridge is the reactive type or AC bridge. This type of bridge is used to measure capacitance and inductance values. The Wheatstone bridge network is based on the parallel resistance circuit as shown in Figure 1. Figure 1. Parallel resistance network. The operation of the Wheatstone bridge is based on bringing point B and D to the same electric potential, that is, EBD equals to 0, by adjusting the variable resistor. For the Wheatstone bridge, point B and D are generally stretched outward, giving the characteristics diamond-shaped bridge circuit shown in figure 2.
Okay, now I'm assuming that you people are having little bit awareness about Western Bridge. Okay, so our today's experiment is to study and understand the working of Western Bridge. Objective is to understand the working principle of the Western Bridge. Okay, so basically this device having name Western Bridge is widely used for measurement of unknown resistance. Unknown resistance. Okay, and this method is having kind of comparison. Okay, as you have seen in the diagram that various registers are there, and in those registers we are comparing this method, this unknown resistance, and through which we are getting the value of unknown resistance. Over here in last video we have seen that diamond structure. Okay, last portion, diamond structure. I'm talking about this one, especially this structure. Okay, here P, Q, R, S. Okay, these four registers are there. Among them, P, Q, R, they are non-resistant. P, Q, and S, they are non-resistance. Among them, Q is variable resistor, and S is unknown resistor. Okay, or even you can consider R. Anyone among them is unknown, and rest of the three are known resistors. Okay, and at center one galvanometer is there through which current will flow. Okay, this method is called as a null measurement. Why? Because just have a look over here in this diagram over here. Okay, here P they have considered as a potentiometer, means variable resistor. Q, R, and S, they are three different registers. Among them, S is unknown, or even you can say R is unknown. Okay, here it's a battery. Black color is a battery. It's a key. Okay, now over here, this consider this central portion, blue color based portion. It's a galvanometer. In ideal condition, it should indicate null. Null means zero. Okay, so it's a null measurement technique. Why? Ideally it should indicate zero always. Okay, if zero is not there, in that case we need to take it to the zero. Okay, it was invented long time ago, 1833, means approximately 190 years ago. Okay, and still it is widely used because of its popularity and usefulness. Okay, how now construction of the Western Bridge. Okay, so just have a look in this diagram. Just have a look in this diagram. Over here it is written, but I am explaining this diagram. E means it's battery. Okay, P, Q, R, S. These are four registers. Among them, P, Q, and S. These three registers are known registers. Okay, and R is unknown register. Dear students, am I audible? Are you getting me?
Yes, sir.
Okay, thank you. So consider positive terminal of battery is connected to the A point, negative terminal of the battery is connected to the C point. Okay, now from A point we are having current is having two paths. Okay, either it can flow across P or it can flow across R. Okay, and then from point B to C through Q, or from point D to C from S register. Okay, over here from point B to D we have connected one galvanometer which is going to indicate 0. in ideal condition. Ideal condition means when bridge is balanced, means what? Consider P, Q, R, S. Each and every register is having 1K value. Consider the scenario. Okay, 1K. So what happens? Current I1 and I2 is having same value. Current I3 and I4 is having same value. At that moment, there won't be any current through the galvanometer. So at that moment, galvanometer is going to indicate zero value. Okay, that is why it is called as a null indication based device. So over here, consider this diagram. R is an unknown resistor that we can find with the help of this equation, PS upon Q. PS upon Q. Okay, PS. So ratio arm base thing. Okay, so that derivation is explained over here. Consider the current through the galvanometer divides two equal magnitude current I1 and I2 is shown over here, I1 and I2. Okay, so I1P is equal to I2R. Just have a look over here. I1P voltage across P resistor is same to the voltage across R resistor. Okay, in ideal condition when galvanometer is having null indication. Okay, same case is applicable to the I3 and I4. Okay, so in balance condition, I1 is equal to I3 is equal to E upon P plus Q, and I2 is equal to I4 is equal to E upon R plus S. Okay, here E is nothing but battery. Just have a look over here. Okay, E is a battery. Okay, so then we are equating both the terms. So P upon P plus Q is equal to R upon R plus S, and finally we are getting this equation, PS is equal to RQ. Among that, as we are interested in R, so P by Q into S. Okay, now its application. It is widely used for the lower value of resistance. It is used for resistive, it is used to acquire data. Okay, so consider light, temperature or strength. They are resistive transducer. Okay, so as a unknown, consider this circuit over here as a unknown value. We are connecting those sensors. Okay, in ideal condition, bridge is designed in a way that it is having null indication, but when parameter gets changed, this bridge gets disturbed, and that output is further given to the instrumentation amplifier. Okay, that circuit you are going to study in op-amp based subject. Okay, even other variations are there with this bridge, through which we can measure capacitance, inductance, frequency, impedance. Okay, over here the galvanometer which we are going to use, it should be very sensitive. Okay, and heating effect should not be there. Okay, various errors it may have, but those errors are not that much affecting our case because we are studying, but temperature as well as resistance variations are creating certain errors, even personal errors. Consider a person who is watching galvanometer, if he makes some error, in that case we are not able to get the full output. Okay, and it's a simulation link. And thank you, dear students. Is there any query, confusion in this explanation?
No, sir.
Okay, now I'm moving to the simulation. Dear student, for this VLab is not available, virtual lab is not available. So, but one nice animation is available. So we are going to see that animation. I have shared my browser. It is visible.
Yes, sir.
So it's a MagLab, Magnet Academy. Okay. So over there they have nice animation regarding Western Bridge. Let me maximize it so that even we can have better visualization. Okay. Now it's a battery. Are you able to see the battery, dear students?
Yes, sir.
Yes.
Okay. R1 and R2 is having some values. R1 is 1K, R2 is 5K, R3 is variable resistor, potentiometer they have used, and R4 is unknown resistor. Okay, current directions they have indicated with arrows. Okay, point A through which two currents are flowing, and over here other directions are shown, point B and direction of the current. Now just have a look on this case. Ideal condition. When ideal condition means we want to find the value of R4. Okay, so R2 into R3, so R3, okay, upon R1, okay, so R2 is having 5, R3 is having 10, and R1 is having 1. So ideally R4, which is unknown, it should have value 50 kilo ohm. Okay, which is in that case current will not pass through the galvanometer. So that I'm just increasing the value. Just have a look on the animation. If R3 is not properly adjusted, in that case what happens? R3 is having higher value. Okay, in that case current will not flow through the galvanometer, and it, as you can see that through these arrows, current is going to pass through the galvanometer. Okay, but when consider the variable resistor, it is having 10K. Okay, what we are doing, we are moving the variable resistor value. Okay, so when variable resistor is having 10K value, at that time bridge is in balanced condition, and due to that current will flow only through the R3, not through the galvanometer. Okay, so in our application what we can do, instead of this R4 we can use RTD, thermistor, strain gauge, LDR. Okay, this kind of resistive elements. So as its resistance will change, over here current fluctuations will be there, and this current fluctuation is given to the instrumentation amplifier. Dear students, is there any confusion in this first experiment?
No,
No,
sir.
sir. No.
No, sir.
So that thing we have seen. Now next is understanding of various instruments. I have shared my screen with you people. Is it visible?
Yes, sir.
Okay, let me add audio. So over here, 4 videos are there. We are going to see those 4 videos along with explanation. So over here, we are going to study CRO power supply multimeter frequency generator. Probably during your first semester, you people have used this device. Am I right?
Yes, sir.
Yes, sir.
Okay. So first is multimeter. Are you able to recall this diagram? This image?
Yes.
Okay. It's a handy multimeter. Current can be measured in series connection and voltage can be measured in parallel connection. We are aware about this thing. Next is power supply. It is quite similar to your mobile charger, but it's a variable power supply. So starting from 0 to 30 volt, 30 volt. Okay, it can give us stabilized output. Stabilized output means AC input, rectifier, so it's a rectifier output. Okay, filter output, voltage regulator, so stabilized regulated output, and over here we are connecting our components. Okay, next is CRO. Okay, what we can do with CRO, dear students?
Input and output waveform.
Yeah, not input. We cannot generate waveform. We can give waveforms. Okay, we can give input signal and we can check its properties. Okay, and just have a look on this thing, on this actual image of the CRO. Okay, so at the time of whenever you are here, I will explain you this thing in detail, how we can do this thing. Even in video, some of the control knobs are covered. Okay, it's a block diagram. It's a, see over here, it's a cathode ray tube. Input signal is given to the cathode heater. Okay, anodes are there. They are nothing but they are making our electron beam sharp. Okay, y axis based details are given to the Y amplifier. X axis based details are given to the X amplifier. Okay, time based amplifier. So they are going to move electron beam horizontally as well as vertically, and finally on the fluorescent screen electron beam move accordingly. Okay, so those details are explained over here, even over here too, and how you can measure amplitude and frequency. Next is a function generator or a frequency generator. It is an image of function generator or frequency generator. Okay, so in video we are going to cover each and every detail. Okay, next is videos. So he's Dr. Mehul B. Shah. He's explaining each and everything through the video. Just have a look on the videos. Are you able to listen the audio, dear students? Is it audible?
Yes.
Yes, sir.
Now same instrument is also used for measurement of resistance. So here you can see that there are marking of resistance on the multimeter. So depending upon the range setting, we can measure maximum resistance. So if so I don't know that what is the value of this resistance. So I assume that it is kilo ohm. So I will set the knob on this 2 kilo ohm, right? And when I apply this terminal of the multimeter across it, it will display uh, some value. So this is the value 0.6667 kilo ohm, right? So now if I connect this range on 200 ohm, then here you can see that it will not display anything, because on this 200 ohm range maximum resistance we can measure is only 200, right? So the display will be blank, it will not display anything. So I have to increase the range. So when I increase the range, you can see that it display 0.660, right? So if I press this button, hold button, it will display constant value, right? Otherwise it is continuously displaying some value, right? If I again increase the range, this is 20 kilo ohm range. So here you can see that the same value, but now the decimal point is shifted. So instead of 0.64, it will display 0.64 because my range has increased. So the precision will reduce. Again I keep it on 200 kilo ohm, right? It will display now same, which is called as a function generator. So here it is the name of the company Syntec, and it is 1 megahertz function generator, and this is the series ST4060. So here you can see that the maximum frequency which it can generate is 1 megahertz, and it can generate sine wave, it can generate triangular waveform, because here there is a symbol of triangular. It can generate square wave, right? And it can generate DC signal also, right? So here depending upon our choice of the signal, we have to press this switch. So right now it is generating sine wave, right? Then whenever I press this button, it will generate triangular waveform. Whenever I press again this, it will generate square wave, right? So this is sine wave, this is triangular waveform, this is square wave, and this is DC. Now here you can see that I can generate output. So this is the terminal where I get the output. We require special type of connector which is called BNC connector. So the shape of this connector is something special, so that it is so it has a center lead, and around that there is a closing. So here we have to insert this, right? So when we insert, then it will take the signal at the output. Now here I can adjust different frequencies also. So depending upon my choice of this, it can generate signal up to 10 hertz, 100 hertz, 1 kilohertz, 10 kilohertz, 100 kilohertz, and 1 megahertz also, right? So I can move left or I can move right, and this is the knob which will vary the frequency. So within 1K I can vary the frequency also, right? So this is the knob. So here this is hertz, it is generating 633 hertz. When I increase this, it will increase frequency, but maximum is 1K. Here it will generate maximum up to 10K, right? So I can select amplitude. So I can select amplitude also, right? yeah, this is for amplitude. So the amplitude of the signal will be decided by my setting of this, right? So it can generate output voltage of up to this much amplitude, 1.2.5 volt, right? So this is how I can generate different frequency signal and different types of signal. Again, this knob will change. If I press this knob, then you can see that this so by pressing this, I can adjust the amplitude range. Just like this frequency range, I can select different amplitude range with the help of this button. Right, so this will be visible when we see CRO. Okay. Which is
Next video.
Most important instrument. It is called cathode ray oscilloscope, CRO. So this is the instrument which can display the waveform. So here you can see that there are two input. This is channel 1 and this is channel 2. So at a time we can display two signal on this CRO. Now at present I have applied sine wave at the input of this channel 1. So this is my connection, right? Now here you can see that there is vertical and horizontal lines on the screen of the CRO. So here my signal, which is a sine wave, has a total 4 so it is starting from this line and it ends up to this line. So my entire signal require 4 division. This is called 1 division, 2nd division, 3rd and 4th. It require 4 division. So, and if I wanted to know that what is the voltage level, then I require to measure uh, this. Here right now channel 1 is 0.5. If I rotate anti-clockwise, it comes to 1 volt. So this meaning of this is that 1 division correspond to 1 volt, and this waveform require 2 division. So the peak to peak value is 2 volt. If I increase this, then here this is 0.5 volt, but it require 4 division. So 0.5 into 4 division correspond to again 2 volt. So like this I can change the range of the vertical bar. Similarly here you can see that this sine wave, so one complete cycle of sine wave has how many horizontal division. So if we start, if we assume, let us consider this peak value, right? So one complete cycle require almost 2 division, 2 horizontal division. So one cycle, this is first peak, this is second peak. So 2 peak require 2 horizontal division, and here it is written as 1 ms. So similar to this vertical rotation, here I can have horizontal rotation. So here this is time per division. So when I set it at this position, it display 1 millisecond. So the frequency of this signal is the time period of this sine waveform is 2 millisecond. So frequency is 1 upon 2 kilohertz. So 1 upon 2 kilohertz is roughly 500 hertz, right? So this is how I can measure the frequency and the voltage. Now there are also other settings. Suppose I press this line.
Next video.
So this is your first lab. So here this is digital multimeter. Now here you can see that there are 4 input where we can give either so at this input we have to apply the voltage which we wanted to measure. This is the common terminal which is always common, and this is normally black. This terminal is for measuring current if it is in the range of 20 ampere, and this terminal is again for the measurement of current if it is in the range of some milliampere. So normally we measure voltage with the help of multimeter. Now here you can see that there are two settings. So first you have to adjust the range. So if we wanted to measure voltage, then we have to approximately know that what is the range of that voltage. And there are again two options, whether voltage is DC. So if it is DC, the range button has to be placed on one of these 5 knobs. So here you can see that this is millivolt, this is volt, this is 20 volt, this is 200, and maximum we can measure 1000 volt. Right. So right now I know that my voltage is less than 20 volts, so I will keep on this. Right. Now here I apply the voltage from power supply. So this is the power supply, and here you can see that there are two terminal, one red, one black. So between these two terminal, I will get voltage within the range of 0 to 32 volt. So this is DC power supply by applet. Now I connect red button. So here I am connecting red button with this, and again I am connecting black wire common with this. So here you can see that the voltage which is supplied is 4.8 volt, and same thing you can see that it is again displayed on the power supply. Right, so this is for the measurement of DC voltage. Suppose I wanted to measure AC voltage, then I have to fix the range over here. So I will measure now power line voltage with the help of this. So here I insert this into this knob, and here you can see that it displays 242 volt approximately. So this is RMS value which is being measured over here, right?
Okay. Next experiment which we are going to see in today's laboratory session I have shared my screen with you people, dear students. Is it visible?
No, sir.
Now,
Yes, sir. Yes, sir.
so it is nothing but to measure tank level using capacitance level probe. It's my index, objective, pre-test theory procedure, VLab simulation link, and post-test. These many things we are going to see in this particular presentation. So our aim is to measure tank level using capacitive probe. Our objective is to review other level measurement methods, and we are going to understand capacitance level probe based method. Okay, so prerequisites are there. One should be aware about various capacitor, various types of the capacitor, working of the capacitor, and parameters on which capacitance is dependent. So just have a look on the beautiful image available on your screen. Okay, it is nothing but capacitor. Okay, even just you can consider other image. Okay, I am skipping this portion. I am not going in depth because being a electronics engineer, I am assuming that you people are having strong background about capacitors. Okay, but for information point of view, I have placed few details over here. First one, in this image, it's a normal capacitors. Okay, while in this image, consider these capacitors. Okay, they are nothing but for They are called as a surface mount component, surface mount capacitors. Okay, so to reduce the size and shape, this type of capacitors are widely used in electronic circuitry. Consider PCB, printed circuit board over there. For industrial applications, these kind of capacitors are used. So consider your mobile phone. If you are going to open your mobile phone over there, you are going to see this kind of components. They are nothing but capacitors. I have just have a look on one video. Why? Because we are going to study capacitance based water level measurement. Okay, so first listen this video carefully. Is it audible?
Yes, sir.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at capacitors to learn how they work, where we use them, and why they are important. Remember, electricity is dangerous and can be fatal. You should be qualified and competent to carry out any electrical work. Do not touch the terminals of a capacitor as it can cause an electric shock. So what is a capacitor? A capacitor stores electric charge. It's a little bit like a battery, except it stores energy in a different way. It can't store as much energy as a battery, although it can charge and release its energy much faster. This is very useful, and that's why you will find capacitors used in almost every circuit board. So how does a capacitor work? I want you to first think of a water pipe with water flowing through it. The water will continue to flow until we shut the valve. Then no water can flow. However, if after the valve we first let the water flow into a tank, then the tank will store some of the water, but we will continue to get water flowing out of the pipe. Now when we close the valve, water will stop pouring into the tank, but we still get a steady supply of water out until the tank empties. Once the tank is filled again, we can open and close the valve as many times as we like. As long as we do not completely empty the tank, we will get an uninterrupted supply of water out of the end of the pipe. So we can use a water tank to store water and smooth out interruptions to the supply. In electrical circuits, the capacitor acts as the water tank and stores energy. It can release this to smooth out interruptions to the supply. If we turned a simple circuit on and off very fast without a capacitor, then the light will flash. But if we connect a capacitor into the circuit, then the light will remain on during the interruptions, at least for a short duration, because the capacitor is now discharging and powering the circuit. Inside a basic capacitor, we have two conductive metal plates, which are typically made from aluminium or aluminum, and these will be separated by a dielectric insulating material such as ceramic. Dielectric means the material will polarize when in contact with an electric field, and we'll see what that means shortly. One side of the capacitor is connected to the positive side of the circuit, and the other side is connected to the negative. On the side of the capacitor, you will see a stripe and a symbol. This will indicate which side is the negative. If we were to connect a capacitor to a battery, the voltage will push the electrons from the negative terminal over to the capacitor. The electrons will build up on one plate of the capacitor, while the other plate in turn releases some electrons. The electrons can't pass through the capacitor because of the insulating material. Eventually, the capacitor is the same voltage as the battery and no more electrons will flow. There is now a build-up of electrons on one side. This means we have stored energy and we can release this when needed. Because there are more electrons on one side compared to the other, and electrons are negatively charged, this means we have one side which is negative and one side which is positive. So there is a difference in potential or a voltage difference between the two, and we can measure this with a multimeter. Voltage is like pressure. When we measure pressure, we're measuring the difference or potential difference between 2 points. If you imagine a pressurized water pipe, we can see the pressure using a pressure gauge. The pressure gauge is comparing two different points also, the pressure inside the pipe compared to the atmospheric pressure outside the pipe. When the tank is empty, the gauge reads 0 because the pressure inside the tank is now equal to the pressure outside the tank, so the gauge has nothing to compare against. Both are the same pressure. The same with voltage. We're comparing the difference between 2 points. If we measure across a 1.5 volt battery, then we read a difference of 1.5 volts between each end. But if we measure the same end, then we read 0 because there's no difference and it's going to be the same. Coming back to the capacitor, we measure across and read a voltage difference between the two because of the buildup of electrons. We still get this reading even when we disconnect the battery. If you remember with magnets, opposites attract and pull towards each other. The same occurs with the buildup of negatively charged electrons. They are attracted to the positively charged particles of their atoms on the opposite plate, but they can never reach each other because of the insulating material. This pull between the two sides is an electric field, which holds electrons in place until another path is made. If we then place a small lamp into the circuit, a path now exists for the electrons to flow and reach the opposite side. So the electrons will flow through the lamp, powering it, and the electrons will reach the other side of the capacitor. This will only last a short duration though, until the buildup of electrons equalizes on each side. Then the voltage is zero, so there is no pushing force and no electrons will flow. Once we connect the battery again, the capacitor will begin to charge. This allows us to interrupt the power supply, and the capacitor will provide power during these interruptions. So where do we use capacitors? They look a little bit different, but they're easy to spot. In circuit boards, they tend to look something like this, and we see them represented in engineering drawings with symbols like these. We can also get larger capacitors, which are used, for example, on induction motors, ceiling fans, and air conditioning units. We can get even larger ones, which are used to correct poor power factor in large buildings. On the side of the capacitor, we will find two values. These are the capacitance and the voltage. We measure capacitance of the capacitor in the unit of farads, which we show with a capital F, although we will usually measure a capacitor in microfarads. With microfarads, we just have a symbol before this, which looks something like a letter U with a tail. The other value is our voltage, which we measure in volts with a capital V. On the capacitor, the voltage value is the maximum voltage which the capacitor can handle. We've covered voltage in detail in a separate video, do check that out, links down below. As I said, the capacitor is rated to handle a certain voltage. If we were to exceed this, then the capacitor will explode. Let's have a look at that in slow motion. Pretty cool. So why do we use capacitors? One of the most common applications of capacitors in large buildings is for power factor correction. When too many inductive loads are placed into a circuit, the current and the voltage waveforms will fall out of sync with each other, and the current will lag behind the voltage. We then use capacitor banks to counteract this and bring the two back into alignment. We've covered power factor before in great detail, do check that out, links down below. Another very common application is to smooth out peaks when converting AC to DC power. When we use a full bridge rectifier, the AC sine wave is flipped to make the negative cycle flow in a positive direction. This will trick the circuit into thinking it's getting direct current, but one of the problems with this method is the gaps in between the peaks. But as we saw earlier, we can use a capacitor to release energy into the circuit during these interruptions, and that will smooth the power supply out to look more like a DC supply. We can measure the capacitance and the stored voltage using a multimeter. Not all multimeters have the capacitance function, but I'll leave a link down below for the model which I personally use. You should be very careful with capacitors, as we now know they store energy and can hold high voltage values for a long time even when disconnected from a circuit. To check the voltage, we switch to DC voltage on our meter, and then we connect the red wire to the positive side of the capacitor and the black wire to the negative side. If we get a reading of several volts or more, then we should discharge that by safely connecting the terminals to a resistor and continue to read the voltage. We want to make sure that it's reduced down into the millivolts range before handling it, else we might get a shock. To measure the capacitance, we simply switch the meter to the capacitor function. We connect the red wire to the positive side and the black wire to the negative side. After a short delay, the meter will give us a reading. We will probably get a reading close to the stated value, but not exact. For example, this one is rated at 1000 microfarads, but when we read it, we get a measurement of around 946. This one is rated at 33 microfarads, but when we measure it, we get around 36. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen now, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, and of course, theengineeringmindset.com.
Dear students, is there any confusion?
No, sir.
Okay, now back to the experiment. Pre-test you can attempt after completion of this laboratory. Even for that, I have provided you the solution to theory. Just have a look on this particular object, okay, where we want to measure the level. So over here, scale is provided. But wherever this kind of scale is not provided at that moment, it becomes little bit difficult. Okay, so continuous level sensors are there. They are indicating exact amount or of a substance in continuous manner. Okay, while second is a point level. They indicate the substance. Okay, if it attains the threshold, okay, at that moment it is going to indicate the value. Okay, so if you want to select particular sensor, then you need to look for various criteria which are listed over here: physical phase, temperature, pressure, vacuum chemistry, dielectric constant of the medium, density, action or noise based thing, vibration, or even mechanical shocks, and tank size. Why? Because we want to measure the liquid level in the tank or even in the vessel. Okay, even for application point of view, certain parameters are there like price, accuracy, response rate, easiness in the calibration, physical size and mounting of the instrument, monitoring or control of the continuous or discrete levels. Okay, next is level measurements. It can be directly or indirect. Just have a look on the directly. Over here, two methods are listed which are important for us. First one is ultrasonic or radar, where we are transmitting waveforms, we are receiving those waveforms, and based on the change in the pattern of the waveform, okay, we can have depth measurement. Okay, even dipstick, resistance steps, sight glass. Okay, so it's a sight glass. Over here we can have direct measurement. Okay, so these are nothing but direct methods, while in indirect, load cell, capacitance, even conductivity, these are nothing but indirect methods. So in load cell we are going to measure the change in the pressure. Okay, while in capacitance, variation in the capacitance. So it is an indirect method for capacitance measurement. Just have a look on this diagram. Over here I am just explaining you the how it works. Over here it's one object in which liquid is filled. It is a non-conductive insulating medium. Okay, now over here this pipe probe is inserted. Okay, if it is a metal tank wall, at that moment this metal tank wall is going to work as a reference plate of the capacitor, while pipe probe is going to work as a first plate of the capacitor. Okay, generally capacitance is dependent on the distance between the plates and effective area of the conductor. Okay, effective area of the conductor. So what happens is this liquid level goes up and down, effective area of the capacitor plate will change. Okay, effective area of the capacitive plate will change, and due to that we can have measurement of the capacitance. That thing I am going to show you through the animation in the VLab simulation. Okay, now measurement of the non-conductive material, measurement of the conductive material, and non-contact measurement. So even consider non-contact non-conductive measurement. Over there the method which we are considering, it can be used, while in conductive measurement probe is having liquid coating. Okay, probe is having coating, so there won't be any short circuiting. Okay, while in non-contact type, proximity of like ultrasonic or infrared transducers can be used. Various advantages are there, but the main advantage is good range for the measurement from few centimeter to about 100 meter. Okay, more rugged, easy to use, easy to clean. Okay, and can be designed for high pressure and temperature applications. Okay, So it can be used for liquid level measurement, powder and granule solids. It can be used for liquid metals at very high temperature, liquefied gases at very lower temperature, corrosive materials like hydrofluoric acids, and very higher pressure industrial processes. Okay, disadvantage, that is not that much relevant. So procedure is available over here for the VLab and simulationing, post test and all other things. So dear students, is there any confusion in this explanation?
No, sir.
Okay, let me go to the VLab link. I don't know why this server is not responding, because just before few moments uh, we have done one experiment on VLab. Okay, so I have already explained each and everything to you people. Okay, now directly move to the simulator. Probably you people have filled that form which is circulated by me. Am I right, dear students? Have you filled that form?
No, sir. I will fill it too.
So complete it as soon as possible, dear student. That data I am collecting for annual day celebration, annual day report. Okay. Different experiment. That is why I was thinking why it is happening. Uh, So I'm just selecting the tank height. It's 500 centimeter, and capacitance probe is having the same height. But if I am selecting more height, then bigger will be the tank, and height of the probe is also more. I am selecting the inner radius. It's a different type of probe. This probe is nothing but first plate is central part and second plate is outer part. Okay, here R2 is mentioned. So this dark line is first plate and the second line is second plate. Okay, so let me increase capacitance, inner radius. Okay, now coffee beans, grains, water, HCl, skimmed milk. Okay, for them you can measure the capacitance. It is saying me that should I confirm the configuration? Yes, I want to confirm the configuration and moving ahead. Okay, here one formula is given for the capacitance through which you can calculate each and everything, and based on that you can have that calculation. So over here liquid level selection criteria are there. Okay, through which you can select up, increase or decrease the liquid level or granule level. Okay, and you can enter your answer. Okay, so you need to repeat this process for 3 different observation. Then our next stage will be visible to us. Okay, so over here capacitance graph is there. As level gets increased, capacitance will also increase. That is the first graph, while second graph is current graph. Here also, as current increases, as level increases, current is also going to increase in milliampere. Okay, so in today, is there any confusion, dear students, in this explanation?
No, sir.
Okay, so today we have performed 3 different experiments. Okay, 6, 7 and 8. And 5 number is present, P number. Your number
Yes, sir.
259. Okay.
Yes, sir.
5, 9, 13. Dear students, yes, dear, may I have mentioned your enrollment number? So I'm again repeating the instruction. Your submission is scheduled in the first week of the May. Try to complete your file, and you should upload. Let me just show you that thing. It's a team, am I right? Over here. No, I'm not talking about this window. It's your team. Okay. Consider your A batch. over here in files, create one folder having your enrollment number and name. Over here I have created one folder called file submission. Okay, so over here create your folder having your name and enrollment number. Let me show you this thing with one another subject. Okay, consider one subject I am teaching in civil department. Okay, so what they did, consider this number, first enrollment number. Okay, 180110. So he has mentioned his enrollment number, then his name, and he has uploaded experiment 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Likewise, you people are supposed to upload your each and every experiment. Okay.
Yes, sir.
Yes, sir. Yes, sir.
You should write each and every experiment in your file, and what to write, how to write, that thing is already mentioned by me in last laboratory. I'm not going through your file in this lab, but in next lab I will check your file up to say up to 7 experiment. Even we have completed 8 experiments. Okay.
Okay, sir.
Thank you for joining me. Have a good time. You may leave now, and just give this message to your other batchmates too.
Thank you, sir.
Thank you, sir.